Hi again, everyone, and welcome to the Virtual Summit, Technology and Solutions for Next-Gen Communication Systems, brought to you, of course, by CTS. I'm Graham Kilshaw with Lectrix, and I hope you've enjoyed the program so far today. For our next presentation, you'll be hearing from Roger Merrill. Roger is the Director of Technical Marketing and Business Development for RF ceramic filter products at CTS. And the first of his two presentations today is What's New in 5G Filters for Sub-6 GHz, Innovations in Universal Footprint Families. Roger, the floor is all yours.
Thank you for joining us at CTS's webinar entitled, What is New in 5G Filters for Sub-6 GHz? We will describe the innovations in our product line. It's important to note that many of these products are new and are not yet included on our website. The contact information for me is accurate, and if you need more information about the specific product or product family, I'm happy to engage with you after this presentation. As you can see, we have a lot of different product families available. These are not even all of them. These are just some of the most relevant and newest ones. For a given frequency band and or for a given power handling, we may in fact have more than one family that is applicable to you. So it's important for us to understand what your requirements are for your system, power levels, performance, even the geographic location where a frequency band is going to be used. The requirements on the filter, in fact, may differ greatly. It's also important to have context about whether the system you're developing is just a point solution for a single band, a single frequency for a single customer, or if you're in fact trying to develop a platform solution that might ultimately be designed to accommodate many different frequency bands, because one of the innovations that CTS has developed is what we call the universal footprint, which is for a given power level. We create a footprint where you can support all of the major frequency bands with a single board design. So in the same way that transceivers are now frequency agile, so too can your board design accommodate any of a number of different filters, all for that same system application. In the most demanding applications, where it may be, for example, a massive MIMO system with extremely close-in rejection requirements, which, let me emphasize, is not true for all frequency bands, but here we've illustrated two frequency bands which are well known to require extreme close-in rejection performance. China Mobile's subset of band 41 being one example where you need a wide passband starting from 2515 megahertz going to 2675 megahertz, and yet only 15 megahertz away on the low side at 2500, you need to be better than 40 dB down. So you need a combination of a relatively small size, and in particular, this part has been optimized for a narrow footprint. So the part's a little thicker, but allows you to finely pitch the parts for neighboring MIMO transmit paths side by side in a tight pitch as might be needed in a massive MIMO system. The other band that's illustrated here is the band 42 used in Europe. Now, band 42 is used in a lot of different parts of the world, but only in the SEPT applications in Europe are the close-in requirements as demanding as is shown here. Both of these are part of the same family. This is the CLB family, which is our ClearPlex. That's our ceramic waveguide technology. These are lightly loaded waveguide designs, so that's what the L is. So Clearplex lightly loaded waveguide bandpass filters is the CLB family. Both of these are 10-pole designs, but I want to make sure I emphasize you're not limited to only 10-pole designs. If you need the highest Q, highest power, highest performance filters, the CLB family is certainly one of the families that we will be discussing here for the best possible performance. And but if you need only a 6-pole design or an 8-pole design, we can certainly address those with the CLB family as well. We also, not shown in either of these cases, but we could certainly also integrate a low-pass filter with these parts as well. But as I said, in this particular case, these two examples were just a bandpass filter alone. Another two families that we have introduced are what we call a single-layer low-profile design. These would be used instead of the CLB when you're looking for similar power and similar performance handling as the CLB, but you need the lower profile approach. The two form factors just differ in the number of poles of the filter and therefore the size. So the ULB is the smaller of the two. So this is universal footprint single layer bandpass filter, and the UXB is the universal footprint extended single layer bandpass filter. The ULB is about 31 by 25 millimeters in size and only about 7 millimeters high. The UXB is about 46 millimeters by 27 millimeters and still also 7 millimeters high. So you've got a very low profile in this case, but it is wider than the CLB that was described previously. As to whether you use the ULB or the UXB, it all comes down to what performance is required. We are showing, for instance, the third one over, UXB 260. This is the same China mobile band that we illustrated on the previous slide. Here you can see it in a single layer low profile version. It required the extra performance of the UXB to achieve the necessary performance that would not have been possible with the ULB. But you can see other examples here. We also should be able to accommodate an interchangeability between the ULB, UXB on a PCB. That is, we can make a integrated solution that could either use a UXB or a ULB, all with a common system PCB that you would have. And we also have the option of integrating low-pass filters with this technology as well. On this slide, we are showing 4 universal footprint families of TDD bandpass filters. In each family, we support all of the major TDD frequency bands that you would need for whether it's 3G, 4G, or 5G applications. The smallest, lowest power solution is the UPB family. Going up in size, performance, and power handling is the USB. Going higher still is the MMB family, and higher still, the highest of all these families is the UCB. The UCB is a ceramic waveguide approach, and it has an integrated low-pass filter, all supporting a universal footprint. And it's roughly the size of the the LB described on the previous slide, but has the added benefit of a little extra performance and low pass filtering, highest power handling, and the highest Q. But you should not be judging these filters, any of these families, based on the power handling per se. It's more what's important is what rejection is required, what insertion loss can be tolerated. In each case, the filters can likely handle much more power than they're optimally suited for in terms of sufficient rejection. Here we're showing side by side the three bands, all in band 48, which is the CBRS band. In fact, band 48, the CBRS band, is available in all four of these families, and it's only which one has the rejection that you need in order to meet what are extremely demanding FCC requirements in order to achieve, for example, the minus 40 dBm per megahertz that the FCC requires at 20 megahertz away from the passband. That is, in this example, at 3530 megahertz and 3720 megahertz on either side of the passband. The UPB is the smallest, lowest power. It's certainly suitable for picocell, femtocell. It can also be used in massive MIMO and is being used in massive MIMO array and other applications when the power handling is relaxed and the close-in rejection is the least demanding. But in many cases, as I said before, you're not judging based on power. You're going to judge based on other factors. So in many instances, a customer may think if their first band that they're working on for a platform happens to be easy, oh, I might be able to get away with the UPB family. But you really need to look at all the bands you are considering utilizing on a given platform and decide based on the more demanding bands. Certainly band 48 is an example of a band where this is important to consider, but it's not the only one. Sometimes band 41, if you're trying to support Wi-Fi co-location, for instance, that might cause you to shift up from the UPB family to the USB family. Similarly, you might think the USB is suitable because it can handle the power that you're looking for. But again, if you truly examine the close-in rejection required, you may find you need the MMB family. The MMB is named for massive MIMO bandpass filter, and it is certainly popular for giving the best performance in the lowest cost, smallest size for massive MIMO applications. Now, as we have shown in the prior two slides, even in a massive MIMO application, you may not be able to solve all your problems in one form factor, at least for some of the most extraordinary demanding frequency bands. So while most of the bands may be satisfied with the MMB, you may have some specific instances where you cannot be truly universal because of the extreme requirements. The China mobile band is an example that demands performance greater than what the MMB would be capable of, for example. The UCB is the only universal footprint waveguide solution and has the integrated low-pass filter. It is a costly option, but at the performance that it offers and the power handling that it offers, it really enables you to develop platform solutions for applications up to 20 watts per antenna path, and is affordable and compact for those applications. So it's what we call the cavity killer. It can compete with the performance of an air cavity, but in a size that's orders of magnitude smaller than an air cavity. So this summarizes 4 TDD bandpass filters, all families, all with universal footprints. Now, it's also important to note that these are not all of the bandpass filter form factors that we have, and there are instances where a customer may need an optimized solution that's as small as it can be for their application. So we do have, they're not part of a universal footprint family, but we do have some in-between sizes. For instance, in between the UPB size and the USB size, we do have some form factors that are about 16 millimeters long in that neighborhood, and we can address solutions on a point basis with that solution, where in those cases where the UPB cannot quite do the job and the USB is too large. Similarly, between the USB and the MMB, we have in-between applications, and larger than the MMB, but smaller than the UCB and less costly than the UCB. We also have options in there. So that kind of gives you the overall summary of the performance that you can get out of TDD bandpass filters from CTS. Now we're at the point of the presentation where we can talk about FDD duplexers. Here too, we have 4 main families of universal footprint FDD duplexers. Again, each of these 4 families are progressively larger in size, power handling, and performance. The UMD, the largest of these, generally has around 2.2 dB insertion loss. Of course, easier bands are less, but all of the bands support receive band isolation of at least 78 dB and generally 80 dB. And that's the S23 response from the TX path to the RX path. This is by far the smallest duplexer available that can achieve that level of performance. It's generally suitable for roughly 5 watt at the antenna applications. The power handling can be used for up to 10 watt at the antenna because it supports up to 20 watts of input power. And sometimes you will find instances where it's appropriate for lower power than even 5 or 10 watts. Again, it comes down to how much rejection you need more than how much power handling you require. The USD, going down in size, the universal footprint small cell duplexer, generally most commonly used in 1 to 2 watt applications. But for instance, in DAS or very wide instantaneous signal bandwidth applications, the USD can be used and is necessary to be used in some sub 1 watt applications. In general, all of the USD family members, which again, we support all the major FDD bands in each of these families. The USD provides 70 dB receive band isolation. Again, that's generally supplied as the minimum for all of the major bands. The UPD family, universal footprint picocell duplexer, provides at least 60 dB receive band isolation. It's certainly optimally used for linearized quarter watt to half watt applications. So where you're looking for high efficiency, carrier grade performance, where when you do the math on the system engineering, you need that 60 dB receive band isolation. This is far and away the smallest solution available. And let me emphasize here that when you look at monoblocks or ceramic filters in general, you need to look at not the size, but you need to look at the performance that they deliver. We have many competitors who offer parts in that 40 to 44 millimeter size, but none of them can guarantee 60 dB receive band isolation across all the major bands, let alone in a universal footprint, let alone with the insertion loss that we're providing. Same is true with the USD, same is true with the UMD. The UFD family is a newer family that is reclaiming some legacy parts. So there were pre-existing family members in this family, but what we did is we collected them together and supplemented with some new parts because we were getting a lot of demand for a smallest and low-performing duplexer to compete against the now discontinued Avago Broadcom duplexers that many customers who have been making femtocell or low-power repeaters applications had been using those parts, and they were left stranded. So now we have this UFD family of parts. They're all under 25 millimeters long. They're all the lowest cost of these options here. And in this is the only case where this applies. It's not a single footprint for all frequency bands. We have one general footprint for most of the low bands and a different one for most of the higher bands that is below 1 gig and above 1.7 gig. But in general, that's a suitable compromise for getting a complete solution across all the major bands in such a small form factor at a very low cost. I'd like to talk to you now about some other innovations that we have beyond just, we'll call it the simple TDD bandpass filters and simple FDD duplexers. So one area that we've now have some solutions in are ultra-wideband filtering. This is where you have an application where you need something either approaching or in some cases even greater than an octave of passband. So an octave would be from, say, in this example, 1 gig to 2 gig. And that's what we're showing on this plot. Now, we elected to accomplish this by offering low-pass filters and high-pass filters. The low-pass filters we created originally to offer as cleanup filters to use with TDD bandpass filters and or FDD duplexers. You can buy those low-pass filters from us on their own, and they have performance that far exceeds the performance of other low-pass filter technologies. Now, that only makes them suitable when you need that performance, but they have very high power handling, up to 20 watts of average and 200 watts of peak input power into those low-pass filters. They have very high Q and very strong rejection. So you end up getting an insertion loss from the low-pass filters alone of around 0.4 dB worst case. And they give close-in rejection all the way past the third harmonic of around 40 dB. So it's both strong rejection and low insertion loss and high power handling all in a single solution. That is the RLF family. It's the rooftop low pass filter family. But so we took that family and combined it with a high pass filter family to create these ultra wideband offerings. This is not yet developed into a complete family of low pass, high pass filters. We already have many, many of the RLF low pass filters for all the major band needs you could have, from as little as 700 meg low pass bands all the way up to 3.8 gig pass bands, and we can of course address even higher frequencies. But by combining them together, cascading them, you can have configurable ultra wideband filtering. So here is the slide with some of these other useful products. The RLF that I mentioned on the previous slide, here it illustrates the performance that's achievable. And you can even see that we have many, many different instances of the RLF family, all in a universal footprint, all in the common form factor. The XCBC family is, again, a very unique product with high power handling, very low insertion loss, very small size, very small cost, or cross-band combining. That's what the XCBC name is for. We have two instances of this product that are universal footprint and interchangeable. One passes the below 1 gig band combined with the high band of 1.7 to 2.7 gigahertz. So for instance, if you have the low band FDD duplexer and a high band FDD duplexer and you want to combine them to share an antenna, you would use an XCBC part. We also have a companion XCBC part that supports 2.7 and below with 3.3 all the way up to 6 gigahertz. This would be especially useful if you're trying to combine a high band like a 5G TDD band, and that could be anything from, say, 3.4 gig to up to a 6 gig band like band 46. So that could be on the high side, and then the low side could be the 2.5 gigahertz bands or below. For instance, Wi-Fi at 2.4 gig and Wi-Fi at 5 gig could be band 41 for the low band and band 42 for the high band. Lots of combinations there. And the two XCBCs can also be cascaded together to create effectively a triplexer, with your three bands being 1 gig and below, 1.7 to 2.7, and a 3.3 to 6 gig band. So those three major coarse bands certainly are attractive for a lot of system applications. Then we have the DPX family. These are diplexers. Diplexer distinguished from a duplexer. A diplexer is combining disparate bands that handle both transmit and receive, whereas a duplexer is for an FDD band where you have a pair of transmit receive used together. A diplexer does not need the same close-in rejection that a duplexer does, because you're not trying to separate receive isolation from the high-powered transmitter. You're simply trying to efficiently power combine two neighboring bands while providing some isolation. In general, the DPX provide between 20 and 30 dB of isolation with generally less than 1.6 dB insertion loss. And these are in a universal footprint for really all of the major FDD and TDD bands that you could imagine that would be especially for adjacent bands. So for instance, band 1 and band 3 are adjacent bands in Europe. Band 2 and and band 66. The PCS and the AWS band for North America are adjacent bands. In Europe, in the low bands, band 8 and band 20 are adjacent bands. These are all just some examples, but all of them are offered in the DPX family and as an interchangeable universal footprint. So these are extremely popular with the multi-band base stations or repeaters or DAS systems that are trying to trying to combine many bands into a single antenna port. I mentioned that the ultra-wideband are comprised of a high pass and a low pass. We're just highlighting that the high passes, of course, are also available on their own. And while these are not strictly part of 5G, in many applications you do need geolocation capabilities. And we have one of the widest selections of high-performance GPS and other GNSS protocols for geolocation. And we have them not only as bandpass filters, but as diplexers. So for GPS, if you need a band L1 and L2 diplex together, we have that. We have L1 plus versus L2 plus L5, and many others. And we have them in different form factors depending whether you need higher performance or smaller size. And we do a lot of customization here to provide exactly the rejection that you're looking for. Another category that are in the nearby frequencies to the geolocation frequencies are the various SATCOM bands. This includes things like Inmarsat and Iridium, and of course, in many instances, these also apply to some 5G bands as well that are neighboring the GPS bands. And so we do have quite a large number of SATCOM duplexers and bandpass filters. And again, we do customize to meet your exact needs. And then we also do military communications, including ITAR applications, both filters and duplexers. I think that is the overview of what we are doing in 5G for sub-6 gigahertz. Now, I don't want you to think that somehow magically there's a ceiling at 6 gigahertz. Many of these products that I've described, if you actually needed something just above 6 gigahertz, for instance, covering the new 6 gigahertz Wi-Fi band, which goes up to 7.125 gigahertz, or even something higher that was in the 7 to 8 gigahertz. We actually have solutions for those needs. And in the other webinar presentation that we're doing today, we describe our support for millimeter wave filters. And strictly speaking, those are up to millimeter wave frequencies. We're going up to 40 gig, but all the way down to below 6 gig with those technologies. So if you have, for instance, an IF that was in 6 to 11 gig or even up to 14 gigahertz, we have solutions for that. And we have solutions above 14, as I said, all the way to 40 gig. So you may also want to listen to that presentation if your needs span for frequencies higher than 6 gig. Thank you very much. Have a great day.
Thank you, Roger. Great presentation. And so to you, the audience, if you have questions for Roger, now is the time to post them into the screen in front of you. If you look in the tray at the bottom of your screen, you'll see a button that says Q&A. That's the button to hit if you've got a question for Roger this afternoon. while you're thinking of your questions, let me quickly recap where we've been so far today. And we have one more presentation coming later today as well. This morning, Roger's colleague Ronan Cohen covered more of the IoT and 5G side of
Hello, have we lost Graham?
I think we lost Graham. See if we can get him back. Well, I don't think he realizes he dropped off. He must have lost his mic, or he possibly lost power again. We've been having some thunderstorms through the area. So
apologies for that.
Are you there? Okay.
I came back, Erica. Thanks for saving it. Sorry for the disruption there, folks. Yeah, we have a lot of storms on the East Coast this afternoon, but I'm back. So 2:45 this afternoon, we have one more presentation from Roger coming up, and that is titled Riding the Millimeter Wave with High Performance Filters, Full Bands and Narrow Subbands. So if you'd like to sign up for that, hop on over to the CTS website or just visit one of the emails from your registration, and there's still time to sign up. Right, let's see. I don't think we have any questions this afternoon. Roger, do you have any final comments before we sign off from this presentation?
Yeah, again, one other thing that is not strictly 5G but is worth mentioning is we can extend down in frequencies. We talked before about what we can go up to, but we can also go down. We've done some things, for instance, in the 450 megahertz band. We've done a number of solutions for the TV white space band. Some people might consider that kind of part of 5G, just an unlicensed portion. Certainly, we will be extending all of our families down to support the 600 megahertz band, which is newly being allocated in North America, and probably something comparable will be allocated in other parts of the world. So, kind of there's, again, it's shades of gray as far as what performance sacrifice can be made, but in general, we can probably do solutions down to about 350 megahertz.
Okay.
I think that's it.
We do have a question, Roger.
Okay.
From Mark Roscoff asks, how high of power might be considered?
Okay. Well, this is a good question, and it also points out a problem that we have when we're communicating with customers, especially about what power they're referring to. Often there's the average power measured at the antenna port. There's the input to the filter, which of course is higher typically by the insertion loss of the filter. So there's the average power into the filter is going to be higher than what comes out because you have filter losses. And then there's peak modulated power, and in many instances for a monoblock, the peak modulated power is in fact the limiting factor. So even though we might be fine with average power, we might even be able to accommodate more average power than we admit on our data sheets. What ends up being critically important is the peak modulated power, since in many cases the power is going straight from a PA on a transmit side into the filter. Often the PSAT, P3dB, or P1dB is a good surrogate for what is the peak modulated power into the filter. We have solutions that support up to 200 watts of peak modulated input power. For instance, the UMD family can support up to that kind of power level. And then some of our waveguide products that were examples, the UCB family and the CLB family being two examples, where we could even go higher than that is certainly possible. In general, power handling scales with the size of the filter. So they're going to be bigger filters at higher power handling. But it's also important to not presume that the power on the data sheet is in fact the limit that even the given filter can handle. In some cases, we have spec'd the data sheet at the limit the power that the filter can handle. But in some cases, we simply specified what I would call the useful power. That is, if the rejection was optimally suitable for a commercial customer to be limited to 2 watts and 20 watts of peak power, average and peak power, we might have put that on the data sheet, but in fact, the part could handle maybe much more than that. So, for instance, there are some UPB parts. Those are the little tiny ones that we described. And we had a customer say, well, I don't really care about the heat rise. I, of course, care about reliability and things like that. For this particular part, and it was a particular one that had a relatively low insertion loss, I need you to give me a special specification that allowed it to handle higher power. And we were, in fact, able to support, I believe it was 6 watts of average power and 30 or 40 watts of, it was 20, 30 or 40 watts, I'm working from memory here, of peak modulated power. Point being, it was much more than the data sheet provided for. In fact, yeah, it was 40. So 6 watts of average, 40 watts of peak power. But in that instance, there was a heat rise of, I believe it was 60 degrees C, meaning if your ambient was 80 C inside your system, the filter would actually be 140 C if you were operating at that full average input power. Now, that's really not a problem for the filter. These ceramic filters are very reliable, even in the presence of high heat, high stressful operating conditions. That, in fact, is also one of the key. The whole reliability profile of ceramic is really best suited for infrastructure or high reliability applications. So we are used in aerospace. We're immune to many of the things that semiconductor technology would be susceptible to. So if you're considering SAW, BAW, F-bar type filters, but this is for a high rel application, or even just we'll call it carrier grade application, where it's going to be always on stressful operating environments, meaning like having transmit at high power all the time, you may find that you don't get the service life or operating life out of a SAW, BAW, or F-bar that you might imagine. And so if you're looking for that more than a 5-year useful life, 10 or 20-year useful life, then you almost certainly want to go to CTS's ceramic filter products. Sorry for the long answer. Hope that was addressing your needs.
Oh, that's great, Roger. Thanks very much. Okay. If you have any other questions, you can certainly reach Roger through the CTS website or places like LinkedIn. And I hope you'll join us again in about 30 minutes for Roger's second presentation of the day, coming up at 2:45. I hope you enjoyed this one. I look forward to seeing you again in about 30 minutes from now. Have a great afternoon.
Thanks, everyone. Bye.